It's my great pleasure to be here this morning. I'd like to offer a welcome to all of those in the rooms that I can see in front of me. I'm terribly sorry that I can't be there in Indonesia to meet you all in person, to talk to you all in person. It's a combination of lots of factors, such as the expense of travel these days, the fact that I have a heavy teaching term, which prevents me from traveling. I work for a university after all, and everybody has to teach. It is interesting that I now have another role within Queen Mary University of London. I'm now Director of Global Engagement as a result of my work in Indonesia. And my role now is to increase international links, including those in Indonesia, which includes master's programs, PhD programs, and research. So I'll certainly be looking forward to engaging with you all in that role in the future. So I think, if it's okay, I will move on to my my talk. I've been asked to give a talk which is an overview of UK policy with respect to climate change and energy generation and use, which, interestingly enough, I'm in the middle of writing a paper on with one of my PhD students who happens to be Indonesian. She came over with me a few years ago. She used to be part of Evie's group. I think she will probably move back to be part of Evie's group in Bryn once she finishes with me next year. So I'm actually writing a paper on this as we speak. So I think from that perspective, I'd like to share my screen and start my talk. Now, can you see this? Can everybody see the presentation? Is that a yes or a no? I need to know if you can see it.
Yes, it's very clear, Alan. Yes, we can hear your voice too.
Okay, so as you can see, I'd like to talk about energy production and climate change well, it's a global problem really, but I'm talking on it from a UK perspective. So here is 800,000 years of CO2 data. And you can see very clearly that over the last 800,000 years, there have been fluctuations. One might even say periodic. In other words, as CO2 comes down, there's some feedback mechanism which pushes it up, feedback mechanism which pushes it down, feedback mechanism which pushes it up. This is the natural CO2 cycle. It keeps the CO2 in the atmosphere averaged at about 220 CO2s per million. And then you can immediately see from about 1950 onwards, massive spike in CO2 in the atmosphere. In fact, a doubling almost of CO2 from the long-term average. And here I've got a little movie which shows the time data of the temperature. This is temperature difference between zero, well, the average starting at time zero, and it's in Fahrenheit because it's from NASA and it's in American. Don't like Fahrenheit? There we go. We have to look at it anyway. And you can see immediately, if the movie shows to you, that it's hot in Africa, which you'd expect. It's cold in the rest of the world, with some warm bits somewhere in the middle of the Atlantic and Pacific. Nope, not the other way around. Pacific and Indian Ocean, a little bit down here, which is part of the Atlantic. Okay. And then as we start to get into halfway through this time series, this would be about the 1940s, you can see that the polar caps are beginning to warm up a little bit. And then as you get further into the 1950s and 60s, it's fairly benign in terms of temperature. There are annual fluctuations, but it doesn't take very long for the average temperature across the whole globe to start coming up in the 80s as we become more and more yellow. Okay. And then as we get into the 90s, you can see there's hardly any blue left on the map. And then we're starting to get red in the polar ice caps for the first time about 10 years ago. And then suddenly in 2021, this is the situation where there's virtually no blue left on the map. In other words, we're looking at an average of 3 to 4 degrees increase in temperature across the globe compared to 150 years ago. Okay, if we look at the sea ice, this is a millions of square kilometers going back the last 30 years. Relatively flat, slight decline perhaps, and then you can see it, that decline accelerates from about 2000, when the spike in the red temperature you could see on the graph was from about 2000 onwards. Land ice is a similar story, a gradual decline over time. I don't know why there's a gap in the data, but there is. Sea level, similar story. Of course, this ice melts, turns into sea. Okay. Sea temperature increases, which is correlated with air temperature and the fact that you don't have any ice caps. And if you go back to look at this graph, you can realize the reason why. Okay, CO2 emission over time has increased since 1800. This is man-made CO2 emission. Coal, oil, and gas being roughly 1/3 each, even as late as 2021. Coal being the most CO2 or polluting fuel form that there is. Relative, fortunately, everything was relatively small, so everything was coal back in 1800, but there was hardly any being produced. Fortunately, oil and gas have come online as we've increased energy usage, but they're still fossil fuels and they still emit carbon dioxide, although less than you would for coal. Now, if you look at fossil fuel consumption in 2021, you can see the big bad boys are America, China, Russia, and India, with Saudi Arabia, and I guess that's Egypt. I'm not 100% sure. Also being bad, and funnily enough, actually, Germany. However, if you look at consumption per capita, then America becomes slightly less important, prevalent, but it's these countries around here. That might be Saudi, actually. I'm not 100% sure which one this is. I need to improve my geography. And then, of course, Australia becomes much worse because it's got a low population density, but burns a lot of coal. So the take-home story from this is that the Nordic countries up here go from really low usage, like overall, to quite high per capita. Okay. A huge population dependent on coal in China. And that's where it's coming. That's where the CO2s are coming from. Okay. And it also exports its emissions to the rest of the world, including Europe. Saudi has got a low population, but an oil-dependent economy. USA have got large emissions, we know that, and a large emissions per capita. But Canada, in terms of emissions, is low compared to America, but they have such a low population density that they become almost the same. Australia, again, a relatively low population, where it goes from relatively low total fossil fuel consumption to per capita being relatively high. And then Russia is dependent on coal and fossil fuels based transport and heavy industry. So I think the take-home message is the worst polluters per capita, the rich nations, and the underdeveloped nations in Asia, South America, and Africa are catching up. So using fossil fuel to develop the economies is something that is happening. Now, if we look at Indonesia in particular, and I've chosen 2015 specifically here because it was a particularly bad year for Indonesia. Now, it isn't as bad as this normally. But if you take total CO2 or greenhouse gas emissions, not only CO2, methane as well, you will discover that in 2015, Indonesia was responsible for 9.2% of the world's emissions. Second in the world, ahead of China. This is per capita. Behind America. Why is this so amazingly high? Well, half of the emissions were from deforestation, and the other half was from the fact that primary energy consumption in Indonesia is almost entirely governed by coal, gas, and oil. Oil being transport mainly. I'm not sure what the gas is used for. I imagine that's industry, and then or electricity generation. And then coal is for industry and power generation. So what can we do about it? Well, we can move electricity generation to a low carbon alternative. We can move to electrified transport. We can move to net zero, which is what my government are currently banging on about. And I will discuss that in a bit of detail later. And then there's some other things like change in industry, which I don't have time to discuss. So let's look at the UK position. So this is from a recent white paper by the UK government, 2021, on energy. Our target is net zero. What that means is that you emit CO2 or greenhouse gases, but there are some processes that are negative emitters. And that it all balances out to mean that you have net zero or even net negative CO2 emission. The way that they want to do this is dramatically reduce reliance on oil and at the same time dramatically increase reliance on electricity, but then make that electricity from renewable or low carbon sources. You can also see that they want to significantly increase the hydrogen economy, although it's not 100% clear how that might happen. It's also not 100% clear how you're going to reduce oil by so much. This will be entirely transport. So how will we move as a nation with such modest increases in electricity usage, if you look? So this goes down by a factor of 4 or 5. And this only goes up by a factor of 2. Where does that modest increase account for transport? That's a difficult one. If we look at electricity generation over time in the UK, you can see that for years we've had static coal generation about 30%. Then in the last 10 years, we've gradually reduced that to effectively 0 now. Okay. We've also kept nuclear relatively exports relatively static, nuclear relatively static. We've got here other, and then here we've got renewables, and then we've got gas. So renewables have dramatically increased, in fact, accounted for the reduction in coal. And if we look at some predictions in the future for electricity generation, this is units of terawatt hour per year. 2020, domestic, non-domestic electric vehicles. And you can see here a dramatic increase in electric vehicles and heating from electric, with a modest increase in other uses. Okay. So going back to this prediction, there is some suggestion that by 2050, electricity demand could be doubled. And this has got to come from renewables, according to the government policy, with some modest increase in nuclear, maybe doubling, maybe a bit more than doubling, okay, with a bit less renewable, okay. There is some discussion about net storage in order to take some of the renewables and store it to even things out. I'll come on to that in a little while. And then we talk about net zero. This is our current emission from transport, power, buildings, waste, industry, aviation, land use. And then the idea is that in 30 years' time, we'll reduce all of these to virtually nothing and actually have a negative bioenergy with carbon capture and storage to accommodate the fact that you've got some above the line. And then this, for aviation and agriculture, it's a bit more complicated because it's very difficult to fly a plane on batteries because batteries are heavy. So you have to use fossil fuels. So it's a bit more complicated, but it's effectively, we're looking at carbon capture and storage again as a possible route to solving the problem. Personally, I think this is science fiction. I don't think it's going to be possible to have carbon capture storage on an industrial scale in the next 30 years. I don't think the technology is there. And I don't think that we as a nation, or indeed as a world, are going to be willing to pay the price for that carbon capture and storage. Now, if we look at electricity generation as a total of CO2 emissions, it's obvious these are fossil and they have the highest. As I've already said, CO2 emissions, by far the highest is coal. Nobody should ever be building coal power stations. And there are some being built in Indonesia as we speak. And so there is an issue there with what do we do with coal? I understand that there are political problems because you need to have energy, you need to have electricity, and it's the cheapest way of doing it. And in a nation in Indonesia that wants to economically develop, you're going to want to do it in the cheapest way possible because then there's more money in the system to spend on other things. There is a poverty problem as well. Biomass co-firing is essentially cheating. What you're doing is greenwashing your coal power stations. What you're doing is you're saying, we'll put 20% of our fuel as biomass, and then the other 80% could be coal. Oh, and the biomass that we're using is from virgin forests somewhere in Canada, which are then replaced with young trees that take hundreds of years to mature. So it's not really, oh yeah, and then we transport those trees across the globe rather than using locally sourced ones. Natural gas obviously is also emitting less, so about slightly less than half, so slightly more than half of the CO2 from coal. The obvious ones that we want to go for are the renewable and the low CO2 ones. So this is solar, several different versions of solar. There's 3, in fact. Geothermal, hydropower, nuclear, offshore wind and onshore wind. Noting that I've already said that biomass is complex because chopping down virgin forests to fire power stations is not the best solution to our energy needs. Okay, just one thing going back here. It is worth noting that whatever way that you make electricity, okay, there are emissions. Because with nuclear, you have engineering of the nuclear power station, lots of cement. You have to transport the fuel from wherever it is that's dug up, which is, there are some mines across the world that are not anywhere near the UK. There are some in America, there are some in Canada, there are some in Africa, for example, some in China and Russia. But the quantity of fuel that's needed is really low in mass and volume compared to the huge quantities that are required for biomass to burn it. And so we're talking about many orders of magnitude difference in weight and volume. And so it isn't too bad in terms of, it could be worse. Okay. Now, if we look at the electricity generation profile in the UK, you can see immediately that we've got nuclear, which essentially is static. If that isn't static, well, you ought to be running, to be honest. It means the reactor's gone wrong. We've got some other hydro and storage and, little bit of geothermal, etc. They're not very interesting. They're tiny. There's a bit of biogas in here. Okay, this one will be biogas, and these two will be hydro and something else. Wind is a big part of it. Solar is a big part of it. Gas is a big part of it. So in total, we have 13 gigawatts of solar panels in service. They only generate about 1.3 gigawatts over a 24-hour period, which is on average, which is pretty low. Okay. Wind, 25 gigawatts of storage, only making 16 gigawatts average over a 24-hour period. But there's actually dropout to 6 gigawatts for several hours on this particular day. And actually, it's a similar story elsewhere. Or the other thing is actually on this. Look at the tiny amount of solar that we get. Absolutely tiny. Essentially, it's negligible. So 2 days of data here, such a short generation profile and such a small amount of electricity is negligible. It's similar elsewhere 9 years ago. This is the daily average in January, February, March, April, May, June, and July, so on and so forth in California. And you can see here that in the winter months, there's not much hydro. There's not much solar. It varies a bit. Okay, May, June, and July is the peak. Why is that? Well, because in California, it's a warm country and a warm state in America, and you want to have air conditioning on. So the peak is in the summer. In the UK, the peak is in the winter because it's a cold country. Okay, but you can see here that, again, solar similarly pretty negligible. And California is a very sunny place. Okay, and actually it's worth wind. Here are 5 different large-scale wind farms. We've got large-scale wind farms across the UK in the gigawatt regime. Okay, so we've got gigawatt wind farms out to sea in the UK. And if you look here, you've got 12th. And this is maybe, I don't know, the 18th, 17th. That's a week's worth of no electricity from wind. And then it's similar here. And it's similar here. So variable, unbelievably variable. So the question is, can we store it? This is a picture of somewhere in Indonesia, in Jakarta. You can see immediately that it's many air conditioning units.
You have 2 more minutes.
Okay, I'm going to overrun a little bit, if you don't mind. Can we store it? Photovoltaics to when we have the load in the UK, which is in the evening. Well, the idea is that you have a power plant, and you have, which is in this case, it's going to be solar or wind, and energy storage facilities, some factories, and some homes, and then you have bidirectional travel of electricity between the energy storage system, the power plant, and all the homes. Let's put in context. This is a newspaper in the UK, which one should never cite, but I am anyway. There's going to be a world's biggest battery to be built in the UK as of last year. It may well be that things have changed and there's bigger ones elsewhere. Sounds like some big numbers, right? We've got £450 million investment for an 890-acre site, which is a big site, which they claim can power 110,000 homes, which is a small city, large town, 350 megawatts of solar generation from 880,000 solar panels and 700 megawatt hours of storage. Okay, that's the area that it's going to take up. I mean, this is London. You might think, oh, it's 5% of London, but London is an enormous city. 5% of London. That's enormous. The annual electricity consumption in London is 40 terawatt hours, or 4.5 gigawatts. If you do the calculation, this battery costing £450 million can store about 10 minutes of London's usage. And what about the rest of the UK? You know, London is not everything. And what about transport? This is my old car. To drive 800 kilometers, 45 kilograms of diesel in a 2-kilogram fuel tank and 5 minutes to refuel, compared to a Japanese car, which is the most popular electric car in my country at the moment. To drive 160 kilometers requires 190 kilograms of battery. and fast charging to 80% takes 40 minutes. So to drive 800 kilometers, are required to have 3.5 hours of charging. Okay, just look at those numbers. Transport long distances with cars, I don't think is going to work unless we can get fast charging and ranges up. So the role of transport, if on loads, if you think about it, if we're going to be energy storing all of this stuff, you know, this photovoltaic, for example, people are out at work in the day and then they get home. What do? They plug in their car, right? They plug in their car, which results in a peak at the same time as the peak. So we need even more storage. So the ultimate point is that we want to avoid this. In my country, we want to avoid this because there aren't any geothermal vents to speak of. In Indonesia, it's an entirely different story where geothermal events are huge. There's a huge number of them. So we actually need to be looking at nuclear, wind, and wind. There's not enough sun. We don't have enough geothermal. Okay. This one here gives static generation. It's the only one out of the renewables that we've got. So this is my government's plan for the next 30 years to do net zero. And the current nuclear position, this is my last couple of slides, so I won't be too much over. You dig up fossil fuels, you send them up to electricity generation to burn, okay? And then you also get electricity from these other sources. That goes to industry, domestic use, and transport, okay? However, electric transport, at least at the moment, is in the minority, which is why it's dashed, whereas fossil fuels, at least at the moment for transport, is the majority supplier of energy, and that's why it's thick. What the government want to do is stop that, okay, to start with. So they want to do this. They want to reduce the reliance on fossil fuels, put some batteries in place to store the energy from here, okay, and eventually they want to reduce reliance completely on fossil fuel for transport, where this becomes solid and the majority of it comes from electricity. They also want to reduce reliance on fossil fuel on industry. The problem is the batteries probably aren't going to work in the current form. We've got a lot of research to do in the next 30 years to make that happen. And we're still reliant on fossil fuels. If we look at this is conventional wisdom. The idea being is you have static nuclear energy, reduction in reliance on fossil fuels, which is for electricity. This box here is electricity. A reduction in the reliance on fossil fuels over time, and an increase in the reliance on renewable energy over time. This is the plan.
I think, yeah.
So just two more minutes.
Yeah.
I want to finish the argument. I started a little bit late because I hadn't planned on introducing I planned on going straight into the talk. So transport reduce reliance on fossil fuels to the point where they are fully reliant on or almost fully reliant on wind. And then domestic gas, which is what we use for heating and cooking. Again, fossil fuels entirely, and then reduce the reliance, and then industry. What we need to be doing is ramping up nuclear. And then at the same time, we ramp up wind. And we convert the wind into hydrogen for domestic gas. And we convert the wind into oil for transport. Okay, and then we use that oil also for industry. This is what we should be doing, ramping up nuclear, because of this is a much better way of storing it than here. So if we go back to this diagram, this is where we are currently. What we need to do is reverse this trend so that the spare capacity, particularly from nuclear, but also from wind and sun, goes into making synthetic fossil fuels, which are essentially carbon zero, because these are essentially carbon zero. And then and then we don't need to change the transport or the domestic or the industry use. And in fact, what we could do is this is perfect storage. It's a liquid or a gas form that we already know how to store. And so actually this can then go back into the grid when we have and use gas or oil power stations to make up the losses when we've got no wind or sun. Okay. So thank you very much, and I'm sorry to be slightly over, but like I say, I hadn't planned on having an introduction.